Hi, welcome to day 3 of the Introduction to Neural Networks. Just to give a quick recap, yesterday we discussed on finding or creating a set of weights such that the error is minimum. What is error here? Error is simply the prediction versus actual of, uh, of our data. So the difference between predicted and actual. The lesser the error is, the better our model will be. And now, in today's video, I would like to go through a practical example on how can we implement it on a very simple function. So let's suppose these are our weights that are inputs. Let's call it as x. Okay, and this is the loss. There are many different kinds of loss functions that we can create, but let's assume that our data is linearly placed such that there is one point in the data set where our loss is minimum. That is, if we have our weights values to be at certain threshold, then the loss is minimum. So this is also known as global minimum. So a linear equation always has a global minima. Let me draw a simple loss curve like this, and we can clearly see that at this weights the loss is minimum. So the way we achieve this is we start at a random point that is at some random weights. Let's assume that we started somewhere around here. Now, since this is a visual representation, we can clearly see that if our x is reduced, then the error will also reduce. Then the loss also reduces. So we can take one step further by decreasing x, and slowly we can keep reducing x such that at this point, if we keep reducing x, the error no longer reduces, but the error increases. Hence, this is the point in the graph where our error is minimum, and this is the weight that we aim to actually have to be multiplied with our input data. So let me pivot from here and show a real-world example of a small function on how can we reach minima through differentiation. So here is a practical implementation of a very small function, 3x squared minus 4x plus 5. Now this example is taken from the Andrews course, and we could see that if our weights or x is between 0 to 5, that is from minus 5 to 5, at some point the error, that is, if we assume y-axis to be the error, then at some point, that is at some x value, the error is at its minimum. So our goal is to find out this point or to reach this point. This can be done in a differentiation fashion. So if you look at derivatives, we can see that as the change, that is the amount of value that we change in order to reflect our weights, that is we basically tune our weights. As it comes to 0, we could see that the effect that this change has over the function will be 0. So if we have our x to be a value of 3, then f of x will be 20. That is, at 3 the loss is somewhere around 20. Now, using differentiation, we need to change this value of x, either increase it from 3 or decrease it from 3, such that we'll have a minimum error or minimum loss. Now, because this is a simple linear function which is plotted, we can clearly see that reducing x value will get us closer to the minimal point. And now in the actual neural networks, this space is not something that anyone can visualize or can be aware of. This is just one dimension, that is, we just change one weight, one x value here, because our equation only has x. So this essentially is changing one weight. But in actual neural networks, we'll have millions and billions of parameters or billions of x to play with. So now, so from the equation, if you could just apply that over here, you could see that if we change the if we nudge or change the x by one value, like by a very small margin, we could see that the x value actually reduced down to 14. Now if we keep doing this iteratively, at some point it keeps reducing. So let me do so yeah, so if we do the change to be 1, so it increased. So if we set the data or the x at 2 by 3, we could see that the error or loss is almost 0. So that means at 2 by 3 point, if our weight is 2 by 3, then the error is lowest. So we slowly tend to achieve this using this differentiation function. And yeah, that is it for today's class. Thank you so much. And I've explained in detail about how we can go from 3 to 2 by 3 in an iterative fashion in order to come to this global minima in tomorrow's lecture. Thank you and take care.